Hello guys, in this video I will solve some examples about identifying concavity and finding point of inflection. We are going to be looking at every type of function and make a table of variations, which is called second derivative test. So let's start with a polynomial function. This is an exercise question, and the same question came 1, 2, 3, 4 times in Voisari so far. So let's find point of inflection and concavity. So concavity means second derivative of the function being equal to either 0 or undefined. Since that's polynomial, second derivative will be equal to 0. We don't have undefined condition. First derivative, 3x squared minus 12x plus 12. Second derivative, 6x minus 12, which is equal to 0. So x will be 2. So is this our point of inflection? So let's put this back in the original function and see if it is defined. So 2 back, 2 cubed, 8 minus 6 times 2 squared plus 12, which will make 8. So we can say x 2 comma 8 is point of inflection. Okay, at this point function is defined, so we have a point of inflection. So second part, let's make a table of variations and identify in concave convex intervals. Okay, f double prime, f from negative infinity till point of inflection, which is to positive infinity. So when you pick a number more than 2, like 3, put it back in the second derivative. 6 times 3, 18. 18 minus 12, 6, which is positive. When you pick a number less than 2, like 1, put it back, it's going to be negative 6, so negative. Negative means function is convex, opening down. Positive means function is concave, opening up. So we can say convex interval is from negative infinity to 2, while concave interval is from 2 to positive infinity. Okay, this is pretty simple when you know the way. You just take second derivative, make a table, that's it. Okay, let's take a look at another ministry exam question. Which of the following functions has a point of inflection? Has a point of inflection. So we will find second derivative of each option and see, equalize it to 0 and see if it changes the concavity. If that point doesn't change the concavity, then we won't talk about point of inflections. Option A. First derivative, 2x minus 1. Second derivative, 2. So actually there is no point. There is no x value that makes second derivative 0. So no need to make a table. We don't have a candidate for point of inflection. B. First derivative, 3x squared plus 2. Second derivative, 6x being equal to 0, then x is equal to 0. We have a number that makes second derivative 0, but does it change just the concavity? Let's see. F double prime, F. So when you pick a number more than 0, like 1, put it back, positive. Pick a number less than 0, like negative 1, negative. So convex, concave, concavity changes. So we have point of inflection. At 0, we have point of inflection. Option B is true then. So why not C and D are false? Let's see. F prime for C, 4x minus 3 cubed. F double prime for C, 12x minus 3 squared. Being equal to 0, then x is 3. When you make a table of variations, pick a number more than 3, like 4, put it back in the second derivative, it's positive. Pick another number less than 3, like 2, since we are squaring it, it's also positive. So concavity doesn't change, so it's always increasing. So like at x equals 3, we don't have point of inflection. Option D. F prime 4x cubed minus 4, f double prime 12x squared. When you equalize second derivative to 0, x will be 0. Let's make a table. When you pick a number more than 0, it will make second derivative positive. Pick a number less than 0. Since you are squaring it, it's also positive. So concavity doesn't change. We don't talk about point of inflection. Only option B has point of inflection. Right? Okay, we have as you can see in option C and D, we have quartic functions and we didn't have point of inflection. So we have a similar question in the exercises part in the book, exercise 20. It's also about quartic function. Sketch a graph of function f that doesn't have a point of inflection at CF of C, even though second derivative is equal to 0, just like in option C and D in the previous question. Even though second derivative is equal to 0, we have a value that makes second derivative equal to 0, but since concavity doesn't change, we didn't have a point of inflection. So we have the same idea here. Second derivative is 0, but concavity doesn't change, so it's not point of inflection. So this is an example to this situation along with these two examples. All right. Okay, let's continue with a question involving an unknown in it. A test prep question and a ministry question, a new ministry exam question. Let A be a negative number. The function is given. Let's identify point of inflection and concavity. Okay, of course, since it's a polynomial function, we will set second derivative to 0. First derivative, 3ax squared plus 6x plus 4. Second derivative, 6ax plus 6 being equal to 0. Then x will be negative 1 over a, right? So let's make a table by using this value only. Okay, second derivative and original function. Now, how I am going to pick a number more than and less than negative 1 over a? I can do that. I can pick a number less than and more than negative 1 over a, because I know that a is negative. I can pick any number and negative number, but it's a little bit confusing if I pick a number and it will take time. I can just use that idea. If you remember in polynomial functions, if there is no double root or stuff, we can check the sign of leading coefficient. So leading term is here 6ax. Its leading coefficient is 6a, whose sign is negative because a is negative. So remember, whatever the sign of leading coefficient is in a polynomial function, if there is no double root, we can start with that sign on the right side of the table. On the right, I'll start with that sign, negative. When I hit the value in between, I change the sign. So I will use that fast way here for solving these kind of questions, because otherwise it's confusing and takes time. Okay, sign of leading coefficient is negative, so on the right I'll start with negative and change the sign when I hit that value. Positive means concave, negative region means convex. So we can say at x equals negative 1 over a, we have point of inflection. I can of course find the point by inserting negative 1 over a back in the function, but it takes a lot of time and effort. I am not asked to find the exact point, so I'm just going to write that the function has an inflection point at negative 1 over a. And about the concavity, function is convex at negative a to infinity, negative 1 over a to positive infinity, and concave, opening up from negative infinity to negative 1 over a. Okay, this is how we solve these kind of questions. We didn't do any we didn't make any difference in the solution in the steps. I just used that fast way. Okay, let's continue solving questions about trigonometric functions. Exercise 11. F of x is equal to x plus 2 cosine x on the given interval. So, since that's trigonometric function, I won't have a double root or stuff. I will equalize the second derivative to 0, make a table. F prime of x is 1 minus 2 sine x, and second derivative will be negative 2 cosine x, right? I need second derivative to be 0. I don't have an undefined condition. Cosine is never undefined. So when you divide both sides by negative 2, cosine x will be 0. In which condition cosine is 0? Cosine is 0 when the angle is equal to pi over 2 plus n pi, where n is an integer, right? So what are the values then? We have an unknown here, we have n. So remember, we solved a similar question in the first derivative test. We have a result involving n, k, whatever. We have to give some values to n. Let's n be, let's say 0. Then what is x? 0 plus pi over 2, pi over 2. So pi over 2 belongs to the given interval, to this interval, so that's true. Give another value, the next consecutive integer, 1. When n is 1, x will be 1 times pi plus pi over 2, 3 pi over 2. 3 pi over 2 also belongs to that given interval, 1.5. What about 2? When I give 2, what happens? 2 plus half, it's gonna be 5 over 2, which is not in the interval. So I'll have just those two values. The other numbers will be outside of this interval. So I have two point of inflection then. Let's make a table of variations to identify concavity. From 0, the first value is pi over 2, second value is 3 pi over 2, and it ends with 2 pi. So I'm gonna pick a number greater than 0, like 1. Put 1 back in the origin, in the second derivative. Negative 2 cosine 1, which will be negative. Since there is no double root, I can change the sign for each number. Negative, positive, negative. So convex, concave, convex then. Now let's write the concavity. Convex intervals from 0 to pi over 2. Union, I have one more region. 3 pi over 2 to 2 pi. Con concave interval, only one region, from pi over 2 to 3 pi over 2. Okay, about point of inflection. So those two will be, at those two we have point of inflection. I'm not gonna find the point. You can find the point by inserting these two values back in the original function. Okay, before I solve next trigonometric function, let me plug the charger. Okay. Sin x plus cosine x. We solved exactly the same question in the first derivative test. Now we're gonna do the same for the second. First derivative of sine is cosine, cosine is negative sine. And second derivative of cosine is negative sine, sine is cosine. Equalize it to 0. We don't have an undefined condition. We have just equal to 0 condition. Okay. Now remember how to solve these type of questions in the first derivative test. We moved one of the functions to the other side. Negative sine x is equal to cosine x. And since we get two different trigonometric functions, to get a single trigonometric function, we divided both sides by cosine to make it tangent. So we can say negative tangent x equals 1. In other words, tangent is equal to negative 1. So what is the reference angle? X is equal to tangent inverse of 1, which is 45, which is pi over 4. So we got our reference angle. Remember, this is not what our original angle is. This is going to help us to find original angle. So in the quadrants, in which quadrant our tangent is negative? I have negative tangent. Tangent is negative in the second and in the fourth. So how do you find the original angle in the second? It's pi minus reference, which will be 4 minus 1, 3 pi over 4. In the last quadrant, the original angle was 2 pi minus reference, which would be 8 minus 1, 7 pi over 4. So I got two values, 3 pi over 4 and 7 pi over 4. Now we are going to use these two to make a table. So we have points of inflection at those two values. Let's make a table from 0 to 2 pi. Okay, we have second derivative here, original function here. Okay, let's pick a value more than 0, like 1. Put it back in the second derivative. Negative sine 1 minus cosine 1. What is the sign of this? Just use your calculator. You're gonna get a negative result. Change the sign at every value because there is no double root. So this is how table of variations look like. So from this table, we will identify concave and convex intervals. Convex intervals 0 to 3 pi over 2, 3 pi over 4. Union, the second part, 7 pi over 4 to 2 pi. Concave interval, the middle region, between 3 pi over 4 to 7 pi over 4. All right. So I think I am done with trigonometric function examples. We have done enough. So let's continue with uh, an inverse function, a rational function, on which interval the function f of x negative 1 over x is concave. So there are two ways of solving these kind of questions. We can take the second derivative, make a table, like we have been doing so far, or as a second way, I can say just graph it because it's a simple graph, right? Because you are supposed to know the parent function. So this is a reflection of a parent function. 1 over x is inverse function whose graph will look like this. Since there is minus in front, we will have a reflection. So you reflect your graph. That's going to be your graph function. So by looking at this function, you can identify the concave interval. So this part is opening up, that part is opening down. So this part is then concave part. So what is the concave part? From negative infinity till 0. Okay, this is pretty simple by using graph. Another function that we can apply its graph instead of taking second derivative. Another ministry question. X to the power of even over odd. Top is less than bottom. So you are familiar with the graph of these type of functions. So we call this as cusp, right? Its graph will be like that. So we have translation 1 unit down. So move your function 1 unit down, make a cusp. Okay, something like, oh, I cannot draw it. Let me try again. It's so slippery in here. It's hard for me to draw it. Okay, let's say something like that. We are looking for concave interval. So the first part is opening down, convex. Second part is also opening down, convex. So this graph is totally a convex graph. We don't have a concave interval. So we will say none. Okay, this is a way. Another way is finding second derivative and making table. Okay, I will solve one last question about the second derivative test before I continue with another part of this section. Okay, first of all, let's talk about this note. For polynomial functions, if f has a local extremum at ab, then there is a value of the function at this point, at the given value, f of a is equal to b, then the first derivative is equal to 0. If there is a point of inflection, then the same point satisfies the original function, and so this point makes second derivative 0. So we already know this information, of course. This is just a reminder. So after by using this information as a reminder, we can solve the next ministry exam question. 2024 first attempt. The original function is given. Find the value of f of negative 3, knowing that the function has a point of inflection at 1, 4. So in order to find the value of the function at negative 3, we should know these unknowns, a and b, right? So we cannot find the answer without knowing a and b. So this is what we have to do first, finding a and b. How are we finding a and b? We are going to find it by using the point of inflection, right? It says there's a point of inflection at 1, 4. point of inflection means it is the point where second derivative is equal to 0. Let's find first derivative. 3ax squared plus 2bx. Second derivative 6ax plus 2b. So if there is a point of inflection, second derivative is equal to 0, at which value? At x equals 1. So when you give 1 to x, 6a plus 2b will be 0. So I got an equation. I will get another equation because this point also is passing through the original function. If it is the inflection point, it should be on the original function, so it should satisfy the original function. So let's use this point in the original function. F of 1, a1 cubed plus b1 squared must be equal to 4. So a plus b equals 4. I got a second equation. Now I have two equations. I will combine them to find the unknowns one by one. I can actually use substitution method here instead of elimination method. Both works, either substitution or elimination. You are familiar with elimination. You like elimination better than substitution, so let me do elimination for you. 6a plus 2b is equal to 0. A plus b is equal to 4. To eliminate one of the variables, we have to multiply one of the equations by the second equation, actually by either -6 or -2, depending on the variable you want to eliminate. If you want to eliminate b, you have to multiply the second equation by -2, right? In this case, 2b and -2b will cancel each other. You'll have 4a equals -8, then a is equal to -2. We got the value of a. By putting this back in the one of the equations, you will find your b. Let me use the second equation, which is easier. A, which is -2, plus b is 4, then b will be 6. So I got the unknown. Now I can evaluate the function at -3. So what is f of x? By using these two unknown, ax cubed, a, which is -2x cubed, plus bx squared, plus b, which is 6x squared. So now we are going to substitute -3 for x. So -2 times -3 cubed plus 6 times -3 squared. -2 times -3 cubed plus 6 times -3 squared. When you type this in the calculator, do the calculations correctly, then you are going to have 108 as an answer.